Hi everyone. Welcome to another statistics research seminar. Today we have the pleasure of welcoming Zhang from UNC Chapel Hill, giving a talk on bet and belief. And so hope you all enjoy that. A little bit of an intro about our speaker. Dr. Zhang is currently an associate professor with tenure at the Department of Statistics and Operations Research at UNC Chapel Hill. Zhang obtained his bachelor's degree from Peking University in 2003, his PhD degree in mathematics from Temple University in 2007, and his PhD degree in statistics from Wharton School, UPenn in 2012. He is an elected fellow of the Institute for Mathematical Statistics. His research includes non-parametric statistics, high-dimensional statistics, and post-selection inference. His research is supported by 5 grants from the National Science Foundation. So I hope you all join me in welcoming.
Thank you. Thanks for the kind of introduction, and thanks for the invitation. It's my great pleasure to present my work here. As Emma mentioned, the title of my talk reads "Bet and Belief," but the first thing I would like to assure you is that this talk is not about gambling, right? And this talk is also not about religion, right? So what are these bet and belief? So they actually came from 2 papers. Bet on independence and belief in independence. The bet here stands for binary expansion testing, and it's about distribution-free test of independence. So so it's the non-parametric dependence detection. On the other hand, belief here stands for binary expansion linear effect, and it's about.
You're doing great. Sorry, I'm just having a bit.
Okay, thanks. Belief is about non-parametric modeling, right? So answering the question, once we have detect some pattern, how can we make use of that, right? So let's begin with bet, right? Again, as I mentioned, it's a test of independence. So let's begin with this concept of independence. As you all know, independence is one of the most important concepts in statistics, one of the most common assumptions in literature. But the thing is, we'll need to be able to verify independence with data. Right. So it's a classical problem, and I carefully studied under many classical models, for example, normal model, GLM, and so on and so forth. But the problem nowadays is that when we doing data, when we see the data, often we don't have model information at the beginning. So the question we are asking is, if we don't have any information about the joint distribution, can we still distinguish dependence from independence? And turns out this is not so easy a problem. We'll start by focusing on a very simple case to study the dependence between 2 variables, 2 continuous variables, and we suppose we have NID observations of them. We'll consider this so-called coupler setting for which the marginal distributions are uniform 0, 1. We can achieve this if we know the marginal distributions. We can use a CDF transformation. If we don't, we can use empirical CDF functions and work with the ranks. But the idea to use coupler is to single out the problem of the joint distribution. So here's a long list of a small proportion of the papers on this topic. You can see that people have been working on the same problem since 1940s, and people are still working on the same problem. And you may wonder why we have to work so hard and working on this same problem for so many years and publish so many papers. And the reason is that if we really don't want to assume anything about the joint distribution, then dependence is something that can go really wild. I'm borrowing this picture to show that dependence can be nonlinear, non-smooth, non-continuous, and sometimes even non-functional. And to see how difficult the problem can be, I'm giving my audience a little quiz. So I have 2 plots of 50 points. Only one of them, X and Y, are independent. In the other plot, X and Y follow some dependent structure. And my question for you is whether you can distinguish the 2. So if you think, okay, if you think plot A is showing some relationship, please raise your hand. Okay, a few, and I guess the rest will choose B. So the answer is actually A. So all the points in A are sampled over the grid lines. Right? Every point is on the line. And on the other hand, the points in B are sampled uniformly from the unit square, which means they are independent. But as you can see that the grid line is so dense that if it's not, the grid lines are not showing, the pattern is not so apparent, right? So that's the point of the designing this structure, this quiz. So I designed this pathological example. I call that bisection expanding across these grid lines. So you can regard this thing as a fractal. So at the first level, what we have is a cross in the unit square. To reach the second level, you take the 4 midpoints here, and you expand the bisectors until they intersect. You can repeat the same process to take the midpoints, expand bisectors to reach d equals 3, d equals 4, and so on and so forth. And there are some interesting properties about uniform distribution over these grid lines. So two of them listed here. First, at the library level D, the marginal distribution are uniform 0, 1. So it's falling to the copula type of situation. On the other hand, if you look at the joint distribution is degenerate. The support is one-dimensional, right? And these two properties will lead to an interesting paradox. That is whether we should describe this uniform distribution over the grid line as strongly non-independent or nearly independent. It appears to be strongly non-independent because this distribution is degenerate, right? If you check the total variation distance from the uniform distribution over the grid line to the uniform distribution over the square, the distance is 1, the maximal possible value. So in that sense, it's far away from independence. On the other hand, this thing also appears to be nearly independent in the sense that the grid lines are getting denser and denser, right? So eventually it's a space filling curve. So that for any point xy in the unit square, if you let d go to infinity, then if the joint probability here converges to x times y, which is precisely the product of marginal probabilities, right? That's the definition of independence, right? So that's what creates a little paradox here. And my question for you again is, which one would you prefer? So let's say just for d equals 4, this pattern here, would you prefer to describe it as strongly non-independent or nearly independent? If you prefer strongly non-independent, raise your hand, please. Nobody. So I guess all of you would prefer nearly independent. But actually, both are correct. There's no actual contradiction, and I'll explain why at a later slide. But not only this is a mental game, this is also an important challenge to existing statistical methods to test independence. So my simulation has shown this shocking fact that with d equals 4, this pattern here, many tests of independence, very popular tests of independence, are powerless even when the sample size is raised to 20,000. And that was shocking to me because we only have 2 variables here. And with 20,000 observation, we can basically plot everything out. We can see the relationship with our eyes. But many tests are saying, no, we cannot detect that. Why is that? Right? There are many reasons, but one important reason is this so-called non-uniform consistency. So the theorem states that if we want to test independence versus dirt away from independence in total variation distance, then for any test you can think about, there exists an alternative distribution such that the test you are thinking about is powerless. The intuition behind this theorem can be easily explained with a fractal. That is, you can consider any good test good test that is universally consistent, so that for any fixed form of a relationship, as n going to infinity, you are guaranteed to have a asymptotic power of 1. Right, so that's good property. But in reality, notice that we never have infinite amount of samples. We always work with a finite n, right? And once you fix the sample size n here, we can always keep expanding this cross. We can keep expanding this cross until my d is large enough that the uniform distribution over the grid lines is so close to the uniform distribution over the square that the test you're thinking about becomes powerless. And this is not only for total variance distance alone. There's a paper by Samuel's group showing the similar result for L2 distance. So it's a general phenomenon. And yes, indeed, we can carry. Yeah, for this, yes, but I can design example because it's easily trackable, and we can characterize this. Yeah, that's a good question. Other questions? Up to you. All right. So I just want to mention that the message from these type of results is quite negative. It basically shows that there's no single test that can be are able to uniformly detect all forms of relationships, not even all levels of this fractal. And in practice, this means a blind spot. Every test has a blind spot. So there's a lot of problem here, and this problem puzzled me for a long time until I came up my kind of solution. That is, if a test exact independence is not possible, then I'll try to test approximate independence. And if one test is not good enough, I'll try to construct a sequence of tests. So this approximation of independence and the sequence of tests are constructed through a filtration approach. And the filtration is constructed based on this classical probability result of a boundary expansion. So which states that now that we are in this calculus, I think marginal distribution are uniform. There's a class. statistical result saying that we can decompose marginal distribution UMV into bits, right? By considering the binary system, right? The sum of IID Bernoulli halves. So this is the binary expansion, and we can truncate this binary expansion at any finite depth t, right? To look at the first few bits. And once we do this truncation, we see easily that UD and VD are nothing but discrete uniform variables over dyadic fractions, right? And another simple fact is that as t goes to infinity, you see that UD converges to U, VD converges to V in probability. But these marginal convergence results do imply a joint convergence, and that is important. That means we can approximate. We can approximate any form of relationship in U and V through that in UD and VD. And this approximation idea is clear. I think it's apparent if we can regard everything as a filtration so that at every level D, we learn 1A, we learn 1B. As D goes to infinity, we learn everything. Right, so that's a filtration idea. But why is this filtration idea helpful? Question?
Would you want to weigh, can they be dependent, right?
They can be dependent, of course.
So that means that AK and BK also need to be.
Yeah, they can be independent as well. But yeah, but then within themselves they are independent.
Oh.
Yeah. That's a good question. Other questions? Okay, yeah, so let's continue. So yeah, we mentioned we build this filtration, but why is this filtration helpful? Right, to see that I'm bringing this famous code, all models wrong, but somewhat useful, right? The point here is that, when I work with, write down UD and VD, I know up front I'm working with the wrong model. UD, VD is not UV, so it's simply wrong, right? But turns out this wrong model can be quite useful in many ways. The first thing it brings us is universality. That is, although the distribution, joint distribution between U and V can be arbitrarily complicated, as long as my D is large, I can always expect a good approximation, right? If you look at the approximation error, it's exponentially small. Right? The second thing is bring us is identifiability. That is, remember, the problem is hard because things can go wild, can go out of control, right? This is because we don't have a model, we don't have a distribution, we don't have a likelihood, we don't have parameters, we don't have anything to track the dependence, right? On the other hand, if we just do this binary expansion approximation, then at every level D, what we have is a 2D by 2D contingency table, which is well-defined model with well-defined parameters, likelihood, and all of a sudden we have everything. And as a consequence of this, we can achieve the desired uniformity. That is, at every level D, where we can guarantee that we can have a uniform consistency against any alternatives that turn away from independence. Remember, this is not possible if we don't do this approximation. Right? So because of these three advantages, this is what I'm proposing to do. I propose to construct statistics that are functions of A's and B's. I call them binary expansion statistics. And the framework to test the approximate independence in UD and VD, I call that the binary expansion testing. So this is my bet on independence. Right? So some remarks before we move on. So we just constructed the filtration as if we know the marginal distribution. But even when we don't know the marginal distribution, we can construct the things, the filtration similarly. The theory and the method also appears to be very similar. Another remark here is that the binary expansion filtration is certainly not the only way to construct a construct a filtration to approximate the problem, but there are certain advantages from this binary expansion approach. So first first advantage is that the sigma field is simple, in a sense that you can the sigma field at every level D is determined by finitely many binary variables. If you think about sines and cosines, the data approximation, the sigma field can be complicated, right? The second point also about simplicity is that the relationship between any two binary variables is linear, in the sense that they are independent if and only if they are uncorrelated. But we know this is not true in general. We know this is true for binomial normal, but it's also true for any two binary variables. And that's important for us because that means second moment is good enough, right? So that's an advantage. A third advantage is connection to bits, right? So we mentioned this binary expansion is essentially bits. And if we construct statistics that are functions of A and B's, can build bitwise operations, and that's computationally efficient. Right? So because of these three advantages, this is what I'm proposing to do study things through binary expansion filtration. And yeah, although couplet theory is well developed, I think this is still new. Now let's see what we can do with this filtration, right? So once we do this binary expansion approximation and do this truncation, then the problem of testing independence becomes a classical problem for testing discrete uniform versus delta wave from discrete uniform. And this is a classical problem. And this calculus and the likelihood for this classical problem is also classic multinomial distribution, right? So for this classical problem with this classical likelihood, we know classical tests such as chi-square tests are uniformly consistent. But why shouldn't we use the chi-square test? For two main reasons. The first thing is that if you look at the degrees of freedom of a chi-square test, it's a 2 to the power d minus 1 square. It's growing exponentially, and it's eventually going to third power. And second important thing is that for practical purposes, the rejection of a chi-square test is not very interpretable, in the sense that you can get a very small p-value from chi-square test. You can claim x and y are related to each other, but this small p-value doesn't tell you how things are related to each other. Right. So this is the two things that we propose to improve upon, and we can show that we can improve these things by grouping the cells in the continuity table through interactions of a binary variable in this filtration. And I'm going to skip many theorems here. Yeah, so essentially the consideration of interactions among binary variables in the filtration will lead to a reparameterization of the multinomial likelihood. And I'm going to illustrate that with the 50 points in the quiz and d equals 2. So it's d equal to, if you consider 2 bits from x, 2 bits from y, what we have is a 4x4 contingency table, right? That's plotted here. The same scatter plot, but you can divide that into 16 cells table. And if you look at the sigma field up to generated by this bits, you see that there are 16 variables here. One of them is trivial. Sorry.
It's not displaying color as well. So.
Oh. I didn't notice. Thank you. That's very helpful. Yeah, hopefully it's better. Yeah. So. Yeah, so 16 variables in the sigma field listed here. One of them is trivial, but each of the non-trivial binary variable in the sigma field is essentially dividing the unit square into half area in white and half area in blue, as you can see. And the new parameters, so-called interaction odds ratios, can be defined as the ratio between the product of white cell probabilities and that of blue cell probabilities. So why are these new parameters helpful? Right. So it turns out that for classical cell probability parameterization, the cell probability carry both marginal and joint information. But for this parameter interaction odds ratios, we can separate the marginal information and joint information. The idea is that if you look at only the interaction with only A's, these three, or the interaction with only B's, these three, contrasting the white region to blue region is providing information about the marginal distribution. Right. On the other hand, if you look at the interaction involving both A's and B's, these 9 of them here, contrasting the white region to blue region is providing information about the form of a relationship. So indeed, we have this theorem showing that all the information about dependence is summarized in this form of a cross interaction odds ratios. And UD and VD are independent if and only if all these cross interactions odds ratios are ones. They are balanced in white and blue. So in a sense, these cross interaction odds ratios are two contingency tables, just as correlations are to multivariate normal variables. If we want to study dependence between variables, we should focus our study on these parameters or statistical functionals. Right? And moreover, sufficient statistics for these parameters are simple. They are so-called symmetry statistics. Basically, this is the difference between the number of points in white and the number of points in blue. Just take the difference that's sufficient for these things. So we should construct our statistics based on these symmetry statistics. So the first method we proposed is the so-called max bet, right? So and the procedure is quite simple. Again, illustrated with the 50 points in the quiz and d equals to 16 cells. So for these 9 cross interactions here, what we need to do is very simple, just to count how many points are in white and how many points are in blue for each of the configurations. And we look for the biggest discrepancy, which happens here, 32 in white, 18 in blue. And then we can compare with, you can use this binomial distribution because under the null, right, we should expect similar number of points in white and blue. We can to get a p-value, right? So this is a binomial p-value. And since we did 9 tests up here, essentially we multiply this p-value by 9 Bonferroni correction for multiplicity to get the overall max bet p-value. So the procedure is quite simple. Just look for the differences, biggest difference, and use Bonferroni. But turns out this simple procedure is actually optimal, minimax optimal, in the sense that under these two mild conditions, we can show that as long as my sample size is growing at this rate, then the power of this max bet can be arbitrarily close to 1. On the other hand, if the sample size grow any smaller, if you change this big O to small O, then no test can be uniformly consistent. The power, asymptotic power is bounded strictly bounded away from 1. So in this sense, this rate is the optimal rate, and using the maximum bet, you can achieve this attain this optimal rate. So go ahead.
How can you compare this theorem to previous model they call us?
Right. Because this is I did approximation here. It's only for fixed level of D here. So it's for the continuous table we have this, but if we look at the whole space, whole entire U and V instead of UD and VD, we don't do this approximation. We can't be uniformly consistent.
That means you actually add some additional structure.
Correct. We are under for every level of approximation we can be uniformly consistent, but overall we don't have a uniformity.
So how can you use your own this new structure because you now set up a new game, but it's not the old game.
Yeah, it's not right. Exactly. Yeah, right. So we can let users to choose in practice choose a meaningful D for their research to do this test, to detect certain resolution, certain form of relationship up to certain resolution based on the data they have.
When people use it, you also need to show like this new structure is the popular ones you listed, not popular, but the ones that you listed.
Yeah.
They cannot be.
They cannot what? Sorry.
They cannot be better than yours.
Oh yeah, so we certainly yeah. So there are some and we'll do some comparison later on. Yeah. That's a great question. Other questions, please. All right. Some remarks on this power result. So first, if you look at chi-square classical test, chi-square test, the consistency requires this many samples, and comparing the rate, we are doing better, right? The conditions I want to mention a little bit. So we have mentioned there are mild conditions. The first condition is basically the alternative distribution, right? That's nothing. Second condition is comparing the maximum signal versus the length, overall length of the signal, right? So this is checking how spiky the signal is, right? So and this is the result basically saying if we have a spiky signal in the dependence, so meaning the dependence only coming from a few interactions, then using the maximum is going to be good, right? And so that's intuitive. That's the intuition here. And indeed, this can be regarded but more general than a sparsity constraint because it can be satisfied when the dependent signal is sparse in among the interactions. This result is also consistent with the result in ANOVA setting. That is, when the signal are square root sparse, using maximum is better than using chi-square. Okay, this rate is also meaningful, basically telling us for a given data set how high resolution you can go in the binary expansion filtration, right? So this rate basically says with n samples you can go up to log n base 2, right? That's the maximal depth you can go in the binary expansion filtration. So this is about the power. Another important gain here is for practical purposes, interpretation. Remember, we mentioned that many tests are not very interpretable, but for max bet here, when we reject independence, we know white and blue regions, right? So we know for what kind of configurations of white and blue, we have more points either in white or blue. And that information is in turn providing information about the form of a relationship between the two variables. So that's a useful interpretation. And I'm illustrating that again with this fractal. right? You can see all these grid lines are falling into the white region of these interactions. And so to calculate the p-value from bet is at depth d plus 1 is very simple. 2 to the power n in the denominator because all the endpoints sampled from the grid line will fall into the white region. This is the number of interactions, and this 2 here is for two-sided test, white and blue. It's a very simple p-value calculation. For the 50 points in the quiz, it's generated with the d equals 5. And if we test the data with 6 bits, then this is the p-value because 2 to 50 is in the denominator, so it's very significant. And that also explains the paradox I mentioned earlier, right? It happens that for this structure d equals 5 for fractal, the first 5 bits are really independent of each other. So in this sense, it's the U and V are nearly independent, right? This basically says if there's any relationship between U and V, the relationship is in the remainder term in the binary expansion approximation, right? So yeah, so this is in the sense that U and V are nearly independent. On the other hand, if you want to test, you want to really know if things are independent or not, you do the test at d equals 6, consider first 6 bits, and then you get this very small p-value, and then you can claim U and V are strongly non-independent, right? So there's no contradiction. It's just at which resolution you want to see the problem, right? So yeah, both are correct. Another perk from this approach is a connection to computing. Remember, if you think of how computer works, right? They work with bits, right? Go ahead.
So what's the p-value at depth 5?
Well, I didn't check, but it's above 0.05, right? Not significant. Yeah, because they are not dependent. Yeah. But d equals 6, you get this. Yeah, let's move on. So computer work with bits, and yeah, the bits for a number in the real number in the binary system is precisely the binary expansion. And one message I really want to say is that bits we use them all the time for computing, but bits are data as well. We can construct statistics with bits. We can make inference with bits. If you think about bet with depth d, it's nothing but testing whether data are independent up to the first d bits. That's exactly what we are doing. Right, and bits are free, right? So I think nowadays everyone process data with a computer, and yeah, and so bits, are really stored in the computer. But for us, freely to use, use freely, and if we construct statistics with bits, then we use bitwise operations. That's on the most fundamental level, and that in turn can provide efficient computation. Yeah, if you think about white and blue, it's just a Boolean operation checking white and blue, right? And yeah, indeed, we have implemented the software with bitwise operators, and I can show that it's 100 times faster than distance correlation, a popular method in practice. By the way, this Zhang here is not me, but my student Zhang, a wonderful student. And I have another wonderful student here, Kentaro. Yeah, so I'm fortunate to have many great students. So now let's do some numerical studies and comparison with the existing methods. So first, power studies. These plots have to look good, right? So yeah, but indeed we have minimaxity, right? We know, we are protected from the worst case. So so among all these cases, compared with all kind of methods, very good. More interesting comparison are on this exploratory analysis. So for practical purposes, remember it's classical textbooks shows that for small data sets we can do this scatter plot matrices. That is, for every 2 variable in the data set we can then make up every 2 variables we can make a scatter plot. We can use our eyeballs to identify interesting patterns. But this is not possible if the data is larger. And so what do people do in practice? So this is a true story from a large lab in genetics. They work with human genes, right? So in the magnitude of this much, right? So what they do is for every pair of gene expressions, you use the test independence. Use distance correlation, which is a very popular method. For 10,000 genes, 10,000 choose 2 is like 50 million. So they got 50 million p-values. They sort the p-values from smallest to the biggest, and focus on the 20,000 most significant pairs. So this is the first step they do, right? The first step, there's no problem. It's distance correlation is very good, right? So this is good. The problem comes from second step. So as you can see, the second step, the only thing they can do is to hire some graduate students to read this 20,000 plots one after another. And you can see this is primarily right. So this is certainly not the best use of the time of our talented students, right? And you can see the source of the problem. The source problem is that the interpretation of these methods are not clear. So people don't know the form relationship, so people have to rely on human eyeballs to identify the form, the relationship. So I want to say BET can help here with its interpretation, with its speed, also with power. And I'm going to illustrate that with a real-time experiment. And by calling it a real-time experiment, I mean I'm going to do the real simulation right here, right in front of you. What I'm going to do is to simulate a data set with 256 observations, 100 variables. The first 10 variables will be generated with as a 5-pair of binomial normal distribution. And you know the relationship is linear, right? And from variable 11 to variable 100, I'm going to randomly pick 2 variables. And I'm going to randomly assign one of the 3 nonlinear relationship to these 2 variables. Can be either parabolic or circular or sine. I'm going to pick one of these 3 randomly and assign to these 2 variables. The goal of the experiment is to identify which 2 variables are nonlinearly related to each other and what their nonlinear relationship is, right? And for replicability and for fairness, also for fun, I'm going to ask you to suggest a random seed to start the simulation, right? And before doing the simulation, the notes on comparison with distance correlation. Distance correlation is very good, but it cannot distinguish the linear dependency and nonlinear ones. That's why people have to hire students to identify, to read these plots, right? So it's not suitable for this task. Okay, another drawback, kind of limitation is that distance correlation is not very fast, in a sense that scanning over this 100 choose 2, about 5,000 pairs is going to take about 3 minutes, and we can compare the speed, right? So that's with that I can, I guess, how do I quit? Okay, good. Yeah, yeah. So now let's generate the data. This is our code, right? Nothing fancy. Not upgrading. So yeah, I need a random seed to start the simulation. So any suggestion? What's your favorite number? 13. Lucky number, right? All right. So let's do this. And this is R, right? Nothing fancy. Generate the data here. You see this Excel file here, right? And the CSV file. Generated today at this is the Eastern time, by the way. But you know it's fresh made data, right? And you know I didn't cheat, right? So if we open this file, we see this is the data with the data we handle every day. We have 256 rows, we have 100 columns, right? I know the first 10 columns are 5 normal variables, right? So you know linear relationship between them. I know from the 11th column to the last column, there are 2 hidden columns here having a nonlinear form of relationship. I guess it's hard to see with our eyes. Yeah, so now let's use the software to identify that. We can use the BET. We have our package, but we also have a GUI for people who are not familiar with our coding. But our package is certainly faster, right? And we also have a C version that's 10 times faster than this. All right, so just load the data here through a few clicks, a few options. The first comparison we want to do is to compare the speed, right? Distance correlation is taking about 3 minutes to finish the process to do the 5,000 tests, right? We can actually count the time together to here. So let me just click submit. 1 second. It's done, right? 2 seconds. Right, so faster than 3 minutes. Right. So now the second task to identify the form of nonlinear relationship. The idea is that the linear relationship can be captured by the interaction of the first bits here. So you can draw a line here, right? But so you can just simply unclick this and check this one and click plot. Here we go. This is saying variable for 74 and the variable for 84. We have more points in the dark region. And from this plot, we can see, from this pattern, you can see this is like a sine curve, right? Right. But it's always good to check, right? So here, I have recorded the which 2 variables are nonlinear related and what their relationship is, right? And we can check it's indeed 74, 84, and indeed it's fine. So it works, right? In 2 seconds, we were able to go over 5,000 pairs, scan, did 5,000 tests, and identify this one pair of nonlinear relationship, right? So
The depth of 2.
depth of 2, yes, that indeed, yeah, good, very good question. Yeah, so nonlinear for this quadratic form, kind of quadratic kind of relationship, we can use depth equals 4 is good enough. 2 is good enough. Right? Yeah. So one thing I mentioned was I'm still not aware yet any other method that can do the same test of the same speed. Yeah, happy to learn more, but I'm hoping this method can help save some time of our students. Yeah, right. So hide this. And I really did apply that to in practice to help the lab in genetics, right? They work with 10,000 genes, right? And that's 50 million pairs, right? If you want to do this EDA with a decent correlation, it's going to take them about 30,000 minutes to finish the process, right? And that's a bit of it formidable, right? For us, it's 300 minutes. Yeah, so further parallel the computing to do things even faster. Yeah, so we can do this quickly. And out of 50 million, we identified 160,000 nonlinear relationships among these genes. And we checked most of which most of which are unknown before. And I'm going to just illustrate with one pair here out of this 160,000. So these 2 genes, for these 2 genes, we have more points in the white region. And it's you can see the cross, the shape is like a cross, right? We got this pair of nonlinear relationship, and then we were curious about why we have a nonlinear relationship between these 2 genes. And yeah, we checked back with the doctors, and it turns out the reason behind here is this a subtype of cancer, this breast cancer. So this is a basal subtype of breast cancer marked in red triangles. It happens that the patients with this subtype of cancer, these 2 genes behave quite dramatically different well, from the rest of the population. So it turns out if you mix the subtypes together, you create this a nonlinear form of relationship, right? And that's the source of relationship and nonlinear relationship. And we kind of identify this nonlinear relationship with that, and that will allow us to track back down what's the reason behind that. And some interesting biological effects are that both of these 2 genes have been individually confirmed to be highly related to this basal subtype of breast cancer, but there's no research yet done their joint behavior. And yeah, so from this EDA, you direct us to this interesting research question: so what's their relationship, joint behavior toward this subtype of cancer, right? And I think yeah, we think this could be important for biological problem, because we can simply do a classification here, right? Just draw a line here, we can classify this subtype of cancer with 90% of accuracy. But if we only use one of the 2 genes, the accuracy is within 70%. Right? So we can gain a lot by doing this. So I've reported all these results to people in medical sciences, and they have been working on the biological problems related to this. Yeah, so this summarizes our first part of the talk. So BET is a new perspective on dependence. So we assume the only assumption we're making is 2 continuous variables and IID observations, but we can achieve uniform consistency, optimal power, clear interpretability, and efficient computation. So the first paper is this one, and there are some follow-up studies, and yeah, our package is also available. So that's the first part. Any questions that I can help with? All right, now let's move on to the second part. I actually think the second part is more interesting. So yeah, so second part is called binary extension linear effect, right? And again, it's answering the question that now that we can identify some nonlinear pattern, how can we make use of that, right? So the idea is that if we detect some correlation, we can build a linear model to make use of the correlation, right? But if we get something nonlinear, what can we do, right? So yeah, and another thing I want to mention is that this is ongoing work, and yeah, there we really have more questions than solutions. So we wrote this first paper, and as an invitation to invite all of you to help us to develop. I think they are interesting. We think they are interesting problems there. So first, collaborators, my student, another one is student, Benjamin Brown, and yeah, great Xiaoli Meng, right? So that's my collaborators on this. And again, it's about modeling complicated form of relationship, but yeah, but let's begin with something simple and something we all know, right? Linear dependence between binomial normal, right? Binomial is linear in the sense that x1 independent if and only they are uncorrelated. And in this case, all the dependence information is summarized in the correlation coefficient, and we can write a conditional expectation of y given x as a linear function, right? But I mentioned a few slides earlier that any two binary variables are also linear in the sense that they are independent if and only if they are uncorrelated. So for the first question we asked back then is, now that binary variables are linear, can we write a linear model out of this, right? Can we write this conditional expectation as a linear function of A? Right, so we studied this a very simple case. Simple case can't be simpler, really. Two Rademacher variables. So this is also requiring A and B are Rademacher variables. So they are binary and they are taking value of plus minus one with equal probability. So symmetric Bernoulli for this. And so that means are zero. For these variables, we know two immediate facts. First, if you square, then you get one. Right, very trivial, right? But the second part is not so apparent. That is, although A and B can be arbitrarily related to each other, if you multiply them together, they'll be independent of A. And that can be easily checked with the correlation. So you're checking covariance. Yeah, AB is also binary, so the product is also binary, so you can check covariance and your expectation O and B are both zero, so yeah, so they are independent. And now we can combine these two facts, right? So if we look at this conditional expectation B given A, you can insert A squared. Right, this is one, right? So just insert that, and you can rewrite this A squared B as AB times A. And after that, you notice that AB and A are independent, right? And you can factor out the expectation of AB to get expectation of AB times A. And if you look at this thing carefully, this is a linear model, right? The slope here is expectation of AB. The intercept here is 0. And what's the error term in this linear model? The error term is precisely the product of A and B, right? Think about this. This is this error term is independent of the predictor, and this error term is explaining the remaining variance in the response B, right? So this is a complete parallel as a normal linear model, right? And when we got this result, then we immediate question for us is, well, this is a too peculiar example, right? Can we generalize this? Right, and yeah, and turns out yes we can, and that's the theorem of belief, binary expression linear effect, showing that relationships between binary variables is linear. Right, so the theorem says that if you have p binary predictors and one binary response, then the conditional expectation is a linear function, and the coefficients in this linear function is nothing but the least squares, right, old friend. And yeah, so yeah, when we got this, we were again a little bit surprised, and yeah, because we were surprised because you know when I was teaching the graduate students, like when I was teaching Cantor, I told him we will have binary outcome, don't fit a regression, fit a probability regression, but don't do least squares, right? And I was wrong. Not only I was wrong, many statistical textbooks were also wrong in the sense the story was not complete, right? So it turns out that when the predictors are also binary, yeah, using least square is optimal in the sense that this is minimizing this any prediction over any function f, right? The conditional expectation is a linear function, right? So this is the thing we want to do. This is optimal, right? And yeah, so that was a little bit surprising to us. And then the question there we asked is, wait, this is so simple. Have you already done that, you know, decades ago? Right. So next thing is we to do is to do a lot of literature research. We found it's they're closely related to many ideas. So there's a Bahadur representation model in modeling a continuous table. There's a Walsh transform in signal processing. There's a so-called linear probability model in econometrics. But there's no systematic study that read things out in this way. Go ahead. Right.
Yeah, like, is it
Linear.
just a fully interactive dummy model?
Right. Yeah.
What they call saturated model.
Exactly. Next slide. Well, 2 slides after I'll talk about this. But there's a way I want to say there are new insights coming from this, and that way we work. Right. This is a saturated model.
I guess the only difference between this and the traditional formulation is because they're parameterizing -1 and 1, but
Yeah. So that leads to different interpretation of the slope. But yeah, we'll talk about this. Right. Yeah. I mean, we're not saying. Yeah. Indeed. I know this is no one. There are people studying, but there I think there are new insights we can provide from
yeah,
here.
because I teach this in my applied research.
Great, good for you. I should really do that. Now, great. So this is the linear relationship, and then so what if things are not binary, right? So we have binary expansion, right? We can we can generate binary variables just by looking at bits, right? Which is at least fast, right? So. All right. So in our first paper, what we did is indeed we just redid the linear model theory, but in bits, right? And there are some interesting comparisons with classical Gaussian linear model. So there are some shared features. There are some unique features. So for both, we show that independence equivalent to correlation. For both, conditional expectation is a linear equation. For both, slopes are 0 related to conditional independence. For both, least square is also MLE, right? So asymptotic normal and efficient. But for uniquely for Gaussian, is for now, up to now, we the residual theory doesn't quite generalize, so open problem number 1. So how to model the remaining variance. This is one question we have. But there are also something unique to by this binary setting. The slopes are within a complex boundary set. All right. So that's this. So there's a comparison, and now let's talk about the saturated model, right? Indeed. So the math here is math here actually trivial. The proof for the lemma and this belief theorem, because we are looking at this tensor product collecting all the interaction terms of the binary of bits. But it happens that because it's a tensor kind of connector product, the dimension of this vector is 2 to the power p. Right, but think about the p binary predictor. How many possible states are there? Also 2 to the power p, right? So this is basically saying I'm basically saying any function of a binary variables is a linear function, right? If you write it in this way, and the conditional expectation is certainly a function of a binary of these a's. So that's why it's also linear. So the linearity is trivial. Right, but still, this is still a lot of insights we can provide from this. And one thing is that although the dimension here is growing exponentially, it's a faithful reflection of the complexity of the problem. Right. Remember, we didn't want to assume anything, but we want to study all forms of relationship. So the problem is indeed exponentially harder, and we expect from this model. So this model provides a unified approach. So the dimensionality is certainly a challenge, but not a drawback. And having said that, regularization is needed after we have this linear least square, right, estimation. Regularization is needed on 2p because the dimension can easily exceed n. But it's feasible, right, because we can shrink things to 0, and it's also meaningful. That's some new insight we can provide. The new insight is a connection with group theory in algebra, the abstract algebra. So this theorem says that if you consider the sigma field generated by p binary variables as a group multiplicative group, then there's a connection between sparsity and the sufficiency. So this the first part of the theorem says that if I have sparsity, if the belief slopes are sparse, so that so sparse that the binary interaction in the group with the 0 slopes forms a true subgroup of the big group. Then condition on this subgroup B and A are independent. So this is the result of sufficiency. It's basically saying all the relationship is summarized in this subgroup. Right. So sparsity implies sufficiency. And the second part says the converse is also true. If we have sufficiency, we have sparsity. If we have this subset S such that B and A are independent conditional S, then outside the subgroup generated by this subset, all the slopes must be 0. Okay, so sufficiency does imply sufficiency. So that provides a basis for regularization. Right, we are doing regularization is a meaningful thing to do. We are shrinking towards the subgroup some sufficiency, something sufficient. The example of subgroup first is trivial thing. So if a slope are 0 for all interaction involving A1, then you can see that all the relationship is summarized in the other P-1 predictors. Right, so this is one case, and there are also some non-trivial subgroups for this one. For example, this one, if you have 3 predictors here, and the non-zero slopes are only within these 3 things, right? These 3 variables, you see, they form a group. They are close under multiplication. If you multiply any 2 of them, you get the other, right? So they form a subgroup. And for this one, there's some implication of this linear model. Basically, this is saying the conditional distribution of the response given these 3 variables is a symmetric. Given this variable is a symmetric with respect of origin. So this means we are doing a shrinkage. We are getting to have a reduced model. It's really meaningful. It can help us to identify some interesting form of relationship. Right. So that's provide some basis of our regularization. So that's some insights, and some other insights we noticed are connection to GLM. One connection is that the GLM, because we are working with a saturated model, so it turns out the GLM is a special case of belief in the sense that for any GLM, for any model, some link function you choose, the slope there is a function of a belief slopes. So so basically different GLM is basically imposing different constraints over slopes over in belief. So this we can use the belief to understand what the GLM is doing, right? And this also represents necessitate the different interpretation of GLM slopes, right? Particularly for interaction term, because different link function is providing different interpretation of the slopes. And another remark here is about complete separation. So when data are most discriminative and GLM-LE it does not converge, right? That's a problem. But for belief, there's no problem. We can have a closed form solution and everything. So that's connection to GLM. And as I mentioned, this is a slide on modeling general dependence. So what if things are not binary, right? So it turns out we can convert things into bits, and we can study this conditional expectation, writing this as a sum of these linear models. This is martingale convergence. Turns out this is martingale, and there's uniform convergence, double limit. So and this is the idea. This result basically says we can study dependence through a divide and conquer approach. That is, we can decompose any form of a nonlinear relationship between U and V into many small linear model over the bits in this joint distribution. We can get optimal estimates over these linear models, and we can aggregate inference to provide the overall inference between U and V. And this approach turns out to have interesting neural network structure. That is, if you can think about it, you can generate nodes from U. That's those bits in A. Those bits from U. That's A, and you can generate the nodes those B's from V, right? And you can just regress each B on all the A's, right? So yeah, you can aggregate information back to model the conditional distribution of V. And we have a martingale convergence guarantee. It's just that, yeah, but here we don't have to worry about any kind of activation function. We don't have to worry about any fancy optimization algorithm. We can just do least square over bits, right? And we know bitwise operation is fast, right? So we are hoping this one can provide some useful interpretation of the black box neural network, right? And we can provide also hoping to provide some computational efficiency, but these are future work and yeah, open problems. Yeah, and invite you to work help us. Yeah. So that's about modeling general dependency. We have some numerical performance showing performance in classification. I think that's robustness is shown here. But one thing I want to mention is application to political science. This is it happens that there's a long debate in political science about using GLM, right? So there's a paper, very famous paper cited Zhang thousands of times, arguing that when we are fitting a binary GLM, we don't need to include the interaction term. And we don't have to include such a term because there's a compression effect of a nonlinear link function. Basically describes that when predictor is large enough to make a fitted probability close to 1, then the effect of other predictor appear to be compressed and smaller. Right. So because of this effect, these two people argued that we don't ever have to include interaction term in binary GLM. Yeah, so so you can see this one may generate some controversy, and indeed, in a few years, people argue like compression-based interaction is an artifact, and we should always include the interaction term and test its significance, right? Yeah, then many years later, people are still arguing back on this thing, saying our compression is theoretically meaningful, and we don't have to include interaction term. And yeah, and then people argue back again, saying we should always include this interaction term. You can see there's a long debate, and yeah, you see the source of the problem, right? The source of the problem is the interpretation of a GLM link function. Every link function is imposing some model assumptions, and that lead to different interpretations and different philosophy, and that will lead to different statistical results. So that's why people have to argue about this all the time. But now we can still resolve all these debates, decade-long debates with belief. We redid the analysis in this Rini paper. Basically, this paper deal with the model how conflict between countries depend on 5 factors. 2 of them are binary, 3 of them are continuous. We basically took the first bit of the 3 continuous predictors and basically fit the belief. That's 2 to the power 5. That's 32 variables there, right? They have about 100,000 observations, totally luxurious situation. But after fitting the model this year, here's the result. All the 5 main effects are Bonferroni significant. There are 6 two-way interactions that are Bonferroni significant. One of them is this marked in red. It's the first bit of the capability ratio of continuous variable. Capability ratio means military capability, right? And the first bit of smaller of the 2 countries' polity score. This is another continuous variable measuring how much dictatorship is in the country. And so this thing is very significant. This is meaningful, right? That means if there's a country that has a dictatorship and there's a huge difference in terms of military capability, then bad things may happen, right? So this result is meaningful, scientifically. Yeah, and yeah, all other actions are not significant, right? So but so this minimal statistical result validates the probability statements, validates inference. But look, we didn't assume anything, right? We are doing this. We didn't have to write into a debate about fitting GLM. We don't have to. We didn't assume any model. We didn't assume any link function, but we can still get useful results, right? It's scientifically meaningful and probability valid probability, right? So that's one thing that belief can help. Right, and so that's my last slide. Summarizing, so we believe can extract linear dependence between variables. It's closely related to many things, but there are so many new insights that we can provide. Yeah, successor-rated model, we can use that to understand GLM and approximate a conditional distribution through neural network structure. Regularizing that is necessary, feasible, and meaningful, and we can provide interpretable inference with a 0 assumption. Right. So yeah, most importantly, I think there are many open problems here, and we warmly invite you to help us to develop all these problems, this framework. And the paper is here, and it's under revision at the annals. So that's the end of my talk. Thank you very much.
So we have kind of out of time, so maybe there's time for questions.
I think it showed like quite a few graphical illustrations on the
Quite few what?
Graphical illustrations
Oh, yeah.
of the dependence on the scale of the on the binary scale of Now I was wondering if there's a way to like transform them back to the actual scale that you.
Oh yeah, you did. Yeah. There is it's a copular, right? The copular transformation, so we can transform back. Yes.
Yeah. How do you know how that would look? Like, so
oh yeah, sure. Actually, yeah, sure. In the paper, I think there are some plots we showed. So,
okay, and you can see the dependence, like the shape,
yeah, indeed.
Yeah, can you explain how you do the regularization?
How to regularization?
Yeah.
Sure, you can use least squares, right? It's an optimization problem. You can add a penalty, L1 penalty, for example.
Oh, sorry, just doing a lasso on the,
Mhm.
on the mid graph.
Yep, indeed, yeah.
Great, let's,
Sorry. But,
someone there?
Do you have a question?
I did.
Okay.
Okay.
Yeah, so a big issue with, the, Bayesian approach, especially large one, can be the computation of the marginal likelihood, over the very high dimensional, or maybe like a polynomial tree, depending on how you're. You talked about, one of the advantages of that being its computability.
Yep.
Do you think it's possible to make like the, polymetry equivalent prior for that?
Yeah.
And then show that like this addresses this really hard
Yeah.
problem equation with similar accuracy?
Yeah, great question. Yeah, indeed. Yeah, we actually we were you know just before coming to here, I was having this discussion with Lima at the Duke, polymetric on this. Yeah, so there I think there are something we can provide yeah for efficient computation and interval.